the search for other worlds, exoplanets, and the quiet hunt for Earth 2. Welcome back to A Sleep in Class, where we turn quiet lectures into restful journeys through history, science, invention, and the wider world. Here, curiosity can slow down, the day can loosen its grip, and there's no test waiting at the end. Tonight, the classroom opens into the search for other worlds, planets orbiting distant suns, hidden in the light of stars too far away to see as anything more than points in the night sky. For most of human history, the planets were only the wandering lights of Earth's own solar system. Mercury, Venus, Mars, Jupiter, and Saturn moved against the background of the stars. They belonged to calendars, navigation, mythology, and early astronomy. Beyond them, the stars themselves seemed fixed and unreachable, bright points too distant to reveal whether they were alone. Modern astronomy changed that picture completely. Many stars are not solitary lights in empty space. They are suns with systems of their own. Around them orbit planets larger than Jupiter, smaller than Neptune, hotter than molten rock, colder than any desert on Earth, locked in permanent day and night, or arranged in systems so compact that several worlds fit inside the orbit of Mercury. These worlds are called exoplanets, planets beyond the solar system. They are found through careful traces rather than simple sight. A star shifts slightly under the pull of an unseen companion. A tiny shadow crosses distant sunlight. A telescope watches brightness change by fractions of a percent. From these faint signals, astronomers measure mass, size, orbit, atmosphere, and sometimes even hints of weather or chemistry. The search for other worlds is not only a search for another Earth, it is a search for context. It asks whether the solar system is ordinary or unusual, whether planets like Earth are common or rare, and whether the conditions that made life possible here belong to one world alone or to a wider pattern in the galaxy. Long before instruments could prove any of this, the question was already waiting inside human thought: whether the stars were merely lights, or whether some of them were suns with worlds of their own. The old question of other worlds. Long before astronomers could prove that planets existed around other stars, the night sky already separated itself into two kinds of lights. Some lights held their positions against one another so steadily that they became the fixed background of constellations. Others wandered. Mercury, Venus, Mars, Jupiter, and Saturn moved against the star field, changing position night after night, and returning in patterns that could be watched, recorded, and eventually predicted. Those 5 planets were known from ancient times. They were bright enough to see without instruments, and they mattered because they did not behave like ordinary stars. Venus could appear as a brilliant morning star or evening star, bright enough to command attention near sunrise or sunset. Mars stood out for its reddish color, which helped later cultures associate it with blood, conflict, and war. Jupiter moved more slowly and shone with a steady brightness that suited its later identification with kingship and supreme gods. Saturn moved even more slowly, marking time on a scale that seemed older and heavier than the quicker wanderers. Mercury stayed close to the sun and was harder to catch, appearing briefly near dawn or twilight, fitting its later association with speed, messages, and thresholds. These were not modern scientific meanings, but they show how closely ancient people watched the sky. The planets were folded into calendars, navigation, ritual timing, astrology, mythology, and early mathematical astronomy. Their names still carry that inheritance. Mercury, Venus, Mars, Jupiter, and Saturn preserve Roman divine names, layered over older Greek and Near Eastern traditions of identifying the wandering lights with gods, powers, and omens. Long before astronomy became a modern physical science, skywatchers were already building careful records of where the wandering lights appeared and when they would return. The old question of other worlds began inside that difference. A planet was not merely a point of light. It was a moving body, and once the planets were treated as bodies, the mind could begin asking whether the heavens contained more than one kind of place. The question was difficult because early observers had no way to separate distant stars from possible distant suns. A star looked like a point. A planet looked like a point. The eye could notice motion, brightness, color, and pattern, but it could not turn a star into a system. For many centuries, the dominant models of the sky placed Earth at the center of motion. The sun, moon, planets, and stars were arranged around it in nested spheres or mathematical paths. These models were not foolish guesses. They were serious attempts to make sense of what the sky appeared to do from the ground. The planets seemed to circle the heavens. The fixed stars seemed to form a great outer background. Human life took place beneath the turning sky, and the visible evidence appeared to put Earth at the center of the arrangement. Still, the old models had trouble explaining everything simply. The planets sometimes slowed, stopped, and appeared to move backward against the stars before resuming their usual paths. Their brightness changed. Their motion required increasingly careful geometry. Astronomers could calculate these patterns with impressive skill, but calculation did not settle what the planets physically were. It predicted the sky without fully revealing the architecture behind it. The telescope began not as an astronomical instrument, but as a practical optical device. In the early 1600s, Dutch spectacle makers were experimenting with lenses that could make distant objects appear nearer. Hans Lippershey, a spectacle maker in Middelburg, applied for a patent in 1608 for an instrument that could make faraway things seem close. The device was often called a spyglass, and its first obvious uses were earthly ones: ships, towers, armies, coastlines, and distant movement across land or sea. News of the instrument spread quickly. Galileo heard of the Dutch spyglass and built improved versions of his own. By 1609, he was turning a telescope toward the sky and recording observations that changed astronomy. The important shift was not only magnification. It was that a handmade tube of glass lenses could turn ancient points of light into physical evidence. When Galileo looked at the moon, it did not appear as a perfect heavenly sphere. It showed rough terrain, shadows, highlands, and unevenness. When he watched Jupiter in January 1610, he found 4 small lights that changed position around the planet from night to night. They were moons orbiting Jupiter, and they proved that not everything in the heavens circled Earth. When he observed Venus, its phases made much better sense if Venus orbited the Sun. The Milky Way which looked like a pale band to the naked eye, resolved into countless individual stars. The change was not merely a change in where Earth sat. It was a change in what the sky was allowed to be. Jupiter could be a center for its own moons. Venus could move through phases. The moon could have mountains and roughness. The Milky Way could be made of stars too numerous for the unaided eye. A device first valued for bringing distant earthly objects closer had opened a deeper universe overhead. Yet, even after the telescope changed the solar system, the stars remained almost impossibly distant. They still appeared as points. No telescope of Galileo's time could show a planet circling another star. No instrument could block the glare of a distant sun and reveal a small companion world beside it. The idea of other worlds could become more plausible, but plausibility was not proof. That difference matters. The search for exoplanets did not begin with a photograph of another Earth. It began with a question that survived for centuries because the evidence was always just out of reach. The solar system had become a family of worlds, but the stars had not yet become other suns with known planets of their own. By the time modern astronomy had accepted that stars were distant suns, the old question had changed shape. The issue was no longer whether other planets seemed possible. The issue was how anyone could detect a dark, small world hidden in the overwhelming light of a star. The problem of seeing the unseen. A planet around another star is not hard to believe in. It is hard to see. Stars produce their own light. Planets usually do not. A planet shines mostly by reflecting starlight, and from many light years away, that reflected glow is faint beside the star that creates it. Even a large planet can disappear in the glare of its own sun. Distance makes the problem sharper. From Earth, a distant planetary system is compressed into an extremely small angle on the sky. The star and its planets may be separated by millions or billions of miles in their own system, but through a telescope, they can appear almost on top of one another. The planet is faint. The star is bright. The space between them is hard to resolve. Direct imaging sounds like the obvious solution, but it is one of the most difficult ways to find an exoplanet. It requires a telescope to separate the planet's light from the host star's glare. Some exoplanets have been found this way, especially young giant planets that still glow with leftover heat from formation, or planets far enough from their stars to be separated more cleanly. Even then, the result is usually not a detailed picture of continents, oceans, storms, or moons. It is often a tiny source of light, studied through brightness, color, position, and spectrum. The first confirmed exoplanets did not arrive as photographs. They arrived through timing. In 1992, astronomers Alexander Walskson and Dale Frail announced planets orbiting a pulsar called PSR B1257 plus 12. A pulsar is not a gentle sun-like star. It is a rapidly spinning neutron star, the collapsed remnant of a massive star. Its radio pulses can be timed with extraordinary precision. Tiny changes in those pulses revealed that something was tugging the pulsar as it rotated. The first confirmed planets beyond the solar system were therefore found not around a living star like the sun, but around the dense remnant of a dead one. That discovery was extraordinary. But it was also strange. It proved that planets existed beyond the solar system, yet it did not answer the most familiar version of the question. Could an ordinary star like the Sun have planets of its own? The answer came in 1995, with 51 Pegasi B. Mitchell-Mayer and Didier Queloz found it orbiting a Sun-like star about 51 light-years from Earth. They did not see the planet directly. They detected the slight wobble of its star through the radial velocity method, watching the star's light shift as it moved under the planet's gravitational pull. The planet, later also named Dimidium, became the first exoplanet discovered orbiting a Sun-like star. It completed an orbit in only about 4 days. That placed it far closer to its star than Mercury is to the Sun. The planet was a gas giant, broadly comparable to Jupiter, but it was not moving in a cold, distant orbit like Jupiter. It was extremely close to its star, intensely heated, and racing through a year shorter than a workweek on Earth. This kind of world became known as a hot Jupiter. Its discovery showed not only that other stars had planets, but that planetary systems could be arranged in ways the solar system had not prepared astronomers to expect. Giant planets did not always stay far from their stars. Some had apparently moved inward or formed into systems that looked nothing like the familiar order of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. The lesson was clear. Exoplanet discovery would not begin by simply looking at distant stars and picking out familiar worlds. It would begin by reading indirect signs: a star wobbling, a star dimming, a pulse arriving early or late, a faint source of heat separated from glare. The hidden planet had to reveal itself through its effects. Once astronomers accepted that, the search became less like ordinary seeing and more like careful listening. The star carried the signal. The planet wrote itself into the motion, timing, and light of something brighter than itself. And when those signals finally became clear, the first great surprise was not another Earth. It was a universe already telling astronomers that other planetary systems could be stranger than anyone expected. The first confirmed exoplanets. The first confirmed exoplanets changed astronomy partly because they arrived in the wrong place. They were not found around a calm yellow star with a familiar arrangement of inner rocky planets and outer giants. They were found around PSR B 1257 plus 12, a pulsar, the collapsed core of a dead massive star, spinning rapidly and sending out radio pulses with astonishing regularity. That regularity made the planets detectable. A pulsar can act like an extremely precise clock. If nothing disturbs it, its pulses arrive in a predictable rhythm. Around PSR B 1257 plus 12, the rhythm shifted slightly. The pulses arrived a little early or a little late in a pattern that matched the pull of orbiting bodies. The planets were not seen. They were inferred from timing, and the timing was strong enough to open the first confirmed planetary system beyond the Sun. The setting made the discovery unsettling. Neutron star is not a gentle birthplace for ordinary planets. It is the remnant of a supernova, a stellar corpse left after violent collapse. Planets there raise hard questions. They may have formed from debris after the original star died. They may have been reshaped from material left in orbit. They may preserve only a strange afterlife of an earlier system. whatever their exact history, they proved that planet formation was not limited to places that looked safe, balanced, or familiar. Then 51 Pegasi changed the question again. The pulsar planets proved that planets existed beyond the solar system, but 51 Pegasi showed that ordinary stars could have them too. It orbited a sun-like star, but the planet itself was anything but ordinary by solar system standards. It was a gas giant moving extremely close to its star, completing a year in only about 4 days. That was the deeper shock. Astronomers had expected giant planets to belong farther out, where colder material made it easier for large worlds to gather mass. Jupiter and Saturn seemed to support that pattern. 51 Pegasi broke it. A giant planet could exist in a tight, hot orbit where no equivalent planet exists in our own solar system. The name hot Jupiter captures the basic idea, but it can make the discovery sound simpler than it was. These worlds were not merely Jupiters placed closer to their stars. Their existence pointed toward movement and disruption in the history of planetary systems. A giant planet might form farther out and migrate inward. Its gravity might disturb smaller planets. Its path might reshape the architecture of the entire system. A solar system was no longer something astronomers could assume stayed neatly arranged after birth. The early discoveries also taught an important lesson about observational bias. The first planets found were not necessarily the most common planets. They were the planets easiest for available instruments to detect. Pulsar planets could be found because pulsar timing is extraordinarily precise. Hot Jupiters could be found because large close-in planets tug their stars strongly and repeat their orbits quickly. The first discoveries were real, but they were also shaped by the tools that revealed them. That made exoplanet science both exciting and cautious. The galaxy had planets, but the first evidence did not produce a simple copy of home. It produced dead star planets and close-orbiting giants. It showed that worlds could survive, form, migrate, or settle into arrangements that seemed strange from the perspective of Earth. From that point forward, the search became less about proving that planets existed at all and more about learning how planetary systems behave. The first confirmed worlds had answered the old question, but they opened a harder one. If giant planets could hide close to their stars, and if planets could be found without being seen, then the next question was how to read the signal clearly. For 51 Pegasi b, that signal came from the wobble of a star. The wobble of a star. A planet does not orbit a perfectly still star. Gravity connects them both. The star is usually far more massive, so its motion is much smaller, but it still responds. Star and planet move around a shared center of mass, a balance point called the barycenter. If the planet is small and far away, the star's motion may be almost impossibly slight. If the planet is massive and close, the star's motion becomes easier to measure. This is the idea behind the radial velocity method, sometimes called the Doppler wobble method. The planet remains unseen, but the star moves under the planet's pull. From Earth, astronomers measure the part of that motion that comes toward us and away from us. The word radial refers to motion along the line of sight. It does not measure the star drifting sideways across the sky. It measures the star's slight inward and outward motion from our point of view. The measurement depends on the Doppler effect. The same basic idea appears in sound when a siren changes pitch as it passes by. But in astronomy, the signal is found in light. When a star moves slightly toward Earth, its light shifts toward shorter wavelengths, often described as shifting toward blue. When it moves away, its light shifts toward longer wavelengths, shifting toward red. Astronomers do not need the whole star to visibly move in the sky. They need the star's spectrum, where dark and bright lines from elements in the star's atmosphere can be measured with great precision. Those spectral lines act like markers. If they slide slightly toward the blue end of the spectrum, the star is moving toward us. If they slide toward the red end, the star is moving away. When that shifting repeats in a regular cycle, it can reveal an orbiting planet. The planet pulls the star one way, then another, over and over again, as both bodies move around their shared center of mass. This is how 51 Pegasi b announced itself. The planet did not appear as a visible world beside its star. The star's light carried a rhythm. The wobble repeated about every 4 days, matching the planet's short orbit. That short orbit mattered. A planet like Jupiter takes nearly 12 years to complete one trip around the sun, so a similar signal would require years of patient watching. A close-in giant repeats its tug quickly, giving astronomers many chances to confirm the pattern. Radial velocity helped move exoplanet science quickly. The first confirmed pulsar planets were announced in 1992. Only 3 years later, the wobble method revealed 51 Pegasi b around a sun-like star. Since then, radial velocity has revealed more than 1,100 confirmed exoplanets. Transit surveys now account for the largest share of discoveries. But the wobble method remains one of the foundation stones of the field. It remains important because radial velocity can reveal facts that a shadow alone cannot. The length of the repeating cycle gives the planet's orbital period. The strength of the wobble gives a clue to the planet's mass. The shape of the signal can show whether the orbit is nearly circular or more stretched out. With enough observations, astronomers can separate a steady planetary pull from some kinds of stellar activity or instrumental noise. The method also has limits. Radial velocity usually gives a minimum mass, not a full exact mass, because the tilt of the orbit matters. If the orbit hides part of the star's motion from our line of sight, the planet may be more massive than the signal alone suggests. Radial velocity also does not usually reveal the planet's size. A planet could be dense and rocky, or larger and gas-rich, unless another method adds more information. That is why early discoveries were shaped by selection bias. Hot Jupiters were loud in radial velocity data. They were massive, close to their stars, and fast enough to repeat their signal quickly. Smaller planets farther out were quieter. A planet like Earth would make the sun move by only a tiny amount, far harder to measure across interstellar distance. The strength of radial velocity is that it turns gravity into evidence. A hidden world pulls. A star answers. Light carries the answer across space. Careful instruments measure the shift. And a planet too faint to see, becomes a repeated pattern in the spectrum of its sun. Yet gravity is not the only way a hidden planet can write itself into starlight. Sometimes the signal is not a wobble at all, but a shadow, a small, regular dimming when a planet crosses between its star and Earth. When a planet crosses the light, a wobble reveals a planet by the pull it gives to a star. A transit reveals a planet by the light it blocks. The planet is still not seen as a detailed world. It passes between its star and the telescope, and for a short time, the star becomes slightly dimmer. The signal is small, but if it repeats at regular intervals, it can become one of the clearest signs that a planet is orbiting there. The idea is simple, but the measurement is delicate. A large planet crossing a small star blocks more light than a small planet crossing a large star. A giant world can produce a deeper dip. An Earth-sized planet crossing a sun-like star produces a far smaller one, roughly like dimming a light by less than 1 part in 10,000. The telescope has to notice that tiny change and then see it happen again after the planet completes another orbit. A single dip in brightness can be misleading. It might come from instrument noise, a star spot, a background eclipsing star, or another false signal. A repeating dip is stronger because it carries time with it. The interval between dips reveals the planet's orbital period, its year. The amount of dimming helps reveal the planet's size. The length and shape of the transit can also give clues about the path the planet takes across the star. The transit method depends on alignment. A planet has to cross its star from our point of view. Many planets do not. They may orbit at an angle that never carries them between the star and Earth, even though they are truly there. Transits, therefore, do not count every planet around every star. They reveal the planets whose orbits happen to be lined up in a way that lets their shadows reach us. When the alignment is right, the method adds information that a wobble alone usually cannot provide. A transit can reveal the radius of the planet. Radial velocity can help measure mass. Together, mass and size can lead to density. Density begins to separate worlds into broad physical types. A dense world may be rocky or metallic. A lower density world may contain large amounts of gas, ice, or lighter material. Transits can also reveal more than size and timing. If a planet has an atmosphere, a small amount of starlight may pass through the thin edge of that atmosphere during transit. Different gases absorb different wavelengths of light. The signal is extremely difficult to measure, but it can carry chemical clues. A transit can therefore turn a distant planet from a measured signal into the beginning of a physical world. The first known transiting exoplanet around a sun-like star was HD 209,458b. Its transit was observed in 1999, after the planet had already been detected by radial velocity. The overlap gave astronomers both mass and radius, making it possible to estimate density. HD 209,458b became an early benchmark because it showed how much could be learned when methods worked together. The transit method eventually became the dominant discovery tool because it could be scaled. Instead of measuring one star's wobble at a time, a telescope could watch the brightness of many stars and search for repeated dips. Planet hunting became a search through thousands of light curves. records of how starlight rises, falls, and steadies over time. Once telescopes were built to watch many stars this way, exoplanet discovery entered a new phase. The search was no longer only a collection of individual breakthroughs. It became a flood of measured shadows, gathered night after night, until the galaxy began to look crowded with worlds. Kepler and the flood of worlds. The transit method became powerful because it could be scaled. A telescope did not have to wait for one star at a time. It could watch many stars at once, measuring their brightness again and again, searching for the same quiet pattern, a small dip, a return to normal light, and then the same dip after the planet completed another orbit. NASA's Kepler Space Telescope was built around that idea. Launched in 2009, Kepler stared at a rich field of stars near the constellations Cygnus and Lyra. Its strength came from patience. By watching the same region continuously, it could detect tiny changes in starlight that shorter or less steady observations might miss. Kepler's central question was how common planets are, especially small planets around other stars. To answer that, it needed a census. The mission watched the brightness of well over 100,000 stars during its primary search. Each star produced a light curve, a record of brightness over time. Hidden among those records were repeated shadows, transits that appeared again and again, faint but orderly. The results changed the scale of exoplanet science. Kepler and its extended K2 mission eventually confirmed more than 2,600 planets and identified thousands more candidates. The larger pattern mattered even more. Planets were common. Small planets were common. Multi-planet systems were common. The galaxy began to look like a place where planet formation was ordinary. Kepler also showed that many systems do not resemble our own. Some planets orbit extremely close to their stars. Some systems are compact, with multiple planets packed inside orbits that would fit well within the inner solar system. Some worlds belong to categories missing from our neighborhood. Super-Earths, larger than Earth, but smaller than Neptune, and mini-Neptunes, smaller than Neptune, but often wrapped in thick atmospheres. That absence is important. The solar system has rocky inner planets, gas giants, ice giants, dwarf planets, moons, asteroids, and comets. But it has no obvious super-Earth and no mini-Neptune in the usual exoplanet sense. Kepler revealed that some of the most common kinds of planets in the galaxy may be worlds we do not have nearby to study up close. One famous early example was Kepler 11, a system with 6 known planets orbiting a sun-like star. Several orbit closer to their star than Venus orbits the Sun. The system showed a different kind of planetary architecture, multiple worlds arranged tightly, moving in orderly paths, packed into a space much smaller than the familiar spread of our own solar system. Kepler candidates still required careful checking. Astronomers had to rule out false positives and confirm that repeated dimming truly came from planets. But Kepler changed the scale of the question. Exoplanet science could now ask how often planets formed, how large they were, how close they orbited, and how varied their systems could be. After Kepler, the search continued with missions such as TESS. the Transiting Exoplanet Survey Satellite. TESS uses the transit method too, but focuses more on bright, nearby stars that are easier to study again with other instruments. In that sense, Kepler and TESS fit together. Kepler revealed the population. TESS helps find nearby targets for deeper follow-up. The flood of worlds produced a planetary census full of patterns, gaps, surprises, and new categories. Once astronomers could count planets by the thousands, they had to start asking what kinds of planets the galaxy had been making all along. The new planet families. Kepler gave astronomers a larger census, and the census required a new vocabulary. The solar system had once supplied the familiar categories: rocky inner planets, gas giants, ice giants, dwarf planets, moons, asteroids, and comets. Exoplanet discoveries did not erase those categories, but they stretched them. The galaxy contained worlds that fit old expectations and many that did not. Hot Jupiters remained important because they had already shown that planets could end up far from where older models expected them to be. Kepler's larger catalog showed something deeper. Many common planets had no clear equivalent anywhere in our own solar system. Super-Earths raised one of the biggest questions. These planets are larger than Earth, but smaller than Neptune. The name can be misleading because super-Earth does not mean a better Earth or even a habitable one. It usually refers to size or mass, not comfort. A super-Earth might be rocky, gas-wrapped, water-rich, frozen, scorched, or unlike anything nearby. The important fact is that our solar system has no clear example, even though this category appears common around other stars. Mini-Neptunes are just as important. These worlds are smaller than Neptune, but often larger than rocky planets, with substantial atmospheres that may contain hydrogen, helium, water vapor, or other volatile material. They occupy a range the solar system does not show plainly. Their existence suggests that many planets fall between the familiar categories of Earth-like rock and Neptune-like ice giant. The galaxy seems comfortable making in-between worlds. Between super-Earths and mini-Neptunes lies one of the major puzzles of planet science. When does a planet keep its atmosphere, and when does it lose it? A young planet near an active star may be stripped by radiation. A planet with stronger gravity may hold gas more easily. Over time, two planets born with similar ingredients may end as very different worlds. One may remain wrapped in a thick envelope. Another may be reduced to a denser rocky core. That divide is sometimes called the radius valley. In exoplanet surveys, planets do not appear evenly at every size. There seems to be a relative shortage of planets in a range between larger rocky worlds and smaller gas-wrapped worlds. That gap may record the history of atmospheric loss, as some planets are stripped down while others keep their envelopes. Some rocky planets orbit so close to their stars that the word year becomes strange. Their orbits can last only days or even hours. Under that kind of starlight, surface temperatures may become extreme enough for rock to melt. These lava worlds are a useful warning. Rocky does not mean Earth-like. A planet can have a solid composition and still be hostile beyond recognition. Tidally locked planets add another kind of unfamiliarity. When a planet orbits close to its star, gravity can slow its rotation until the same side always faces the star. One hemisphere may remain in constant daylight, while the other remains in constant night. The boundary between them is sometimes called the terminator, a permanent zone between day and night. If an atmosphere or ocean moves heat around the planet, that boundary may become scientifically important. Tidal locking is not automatically a death sentence for habitability, but it changes every question about climate. Water-rich worlds are another possibility, though often difficult to confirm. Some planets may contain far more water than Earth, perhaps as deep oceans, high-pressure ice layers, steam atmospheres, or mixtures of rock, water, and gas. These are not simple ocean planets from fiction. Their interiors may be strange, their surfaces uncertain, and their atmospheres hard to read. There may also be rogue planets, worlds not bound to any star. Some may have been thrown out of young systems by gravitational encounters. Others may have formed in unusual ways. Without a parent star, they do not have days, years, or sunlight in the ordinary sense. They are difficult to detect, but gravitational microlensing and infrared observations can sometimes reveal them. A planet, in the broadest sense, does not always live under a sun. These categories are tools, not final boxes. They help astronomers ask how planets form, how they migrate, how atmospheres survive, how stars shape nearby worlds, and why some systems become orderly while others become compact, extreme, or disrupted. By this point, the search for other worlds had changed again. The question was no longer only how to find planets or how many existed. It was what kind of planets the galaxy was making, and whether any of those worlds could hold conditions gentle enough for life. What makes a planet habitable? After the flood of new planet families, one question begins to narrow the search again. Among giant worlds, rocky worlds, gas-wrapped worlds, lava worlds, water-rich candidates, and planets without suns, which ones could actually support life? The most familiar starting point is the habitable zone, the region around a star where liquid water could exist on a planet's surface if the planet has the right atmosphere and pressure. The phrase is useful, but limited. A planet in the habitable zone is not automatically habitable. It is only in a place where surface liquid water might be possible. Earth sits in the sun's habitable zone, but distance is only one part of the reason Earth works. It has a protective atmosphere, enough pressure for liquid water, active chemistry, sunlight, internal heat, and a long period of relative stability. Life, as we know it, needs liquid water, usable energy, and chemical ingredients. A living world also needs those conditions to last. Venus and Mars make the warning clear. Venus orbits closer to the sun and became extremely hot under a thick carbon dioxide atmosphere. Mars orbits farther out and has a thin atmosphere, low pressure, and a cold surface where liquid water is not stable for long today. Both are near Earth in the same solar system, yet neither is a second Earth. Atmosphere can decide the fate of a world. It can warm a planet through greenhouse gases, shield the surface from radiation, and create pressure that allows liquid water to remain on the surface. Too little atmosphere can leave a world cold and exposed. Too much, or the wrong balance, can trap heat until the surface becomes hostile. Planet size shapes the story as well. A small planet may struggle to hold an atmosphere over billions of years. A larger planet may hold gas more easily, but if it becomes too gas-wrapped, it may not have a familiar rocky surface at all. Gravity, chemistry, geology, and internal heat all help determine what kind of world a planet becomes. The star sets another boundary. A steady star gives a planet time. A violent or highly active star can strip atmospheres, bathe nearby worlds in radiation, or make surface conditions unstable. Habitability may require millions or billions of years of workable conditions, not merely a brief moment in the right orbit. A habitable planet is therefore not defined by one feature. It is built from a chain of conditions: orbit, atmosphere, pressure, water, chemistry, energy, stability, and time. The habitable zone helps astronomers know where to look first, but it does not finish the question. Many of the most tempting targets orbit the smallest and most common stars in the galaxy. Those stars offer great promise: many planets, close orbits, and long stellar lifetimes. They also bring some of the hardest problems in the search for another living world: red dwarfs and difficult promise. Many of the most interesting planets in the search for life orbit red dwarf stars, also called M-dwarfs. These stars are smaller, cooler, and dimmer than the Sun. They are also extremely common. If the galaxy contains many small rocky planets, a large share of them may orbit stars like these. Red dwarfs offer several advantages to planet hunters. Because the star is small, an Earth-sized planet blocks a larger fraction of its light during a transit. Because the star is less massive, an orbiting planet can make it wobble more noticeably. These effects make small planets easier to detect than they would be around a larger sun-like star. They also live for a very long time. A small red dwarf burns its fuel slowly, far more slowly than the Sun. That long lifetime gives planets an enormous window of possible stability. If a planet can keep the right conditions, its star may shine steadily for billions or even trillions of years. But the promise comes with difficulty. Because red dwarfs are dim, their habitable zones sit close to the star. A planet must orbit nearby to receive enough warmth for surface liquid water to be possible. Close orbits make planets easier to find, but they also create problems. The same gravity that keeps a planet near its star can slow the planet's rotation until one side always faces the star. That condition is called tidal locking. One hemisphere may remain in constant daylight while the other remains in constant darkness. The day side could be hot and exposed. The night side could be cold enough for gases to freeze out, depending on the atmosphere. Between them lies the terminator, the boundary zone between day and night. If the planet has a thick enough atmosphere or ocean, heat might circulate from the day side to the night side. Without that movement, the climate could become extreme. Red dwarfs can also be active, especially when young. Powerful flares and high-energy radiation may strike close-in planets. Over time, that activity can damage or strip atmospheres. A planet in the right orbit may still lose the air and pressure it would need for liquid water on the surface. Habitability around red dwarfs, therefore, depends not only on distance, but on whether a planet can survive its star's behavior over time. TRAPPIST-1 shows both the promise and the difficulty. It is an ultra-cool red dwarf, about 40 light-years away, with 7 known Earth-sized planets. Several orbit in or near the region where liquid water could be possible under the right conditions. The system is compact, with planets packed close to their star and to one another. It became one of the most important natural laboratories for studying small planets around small stars. Yet, TRAPPIST-1 has not given a simple answer. Earth-sized does not mean Earth-like. A planet in the right region may have no atmosphere, or an atmosphere unlike Earth's, or surface conditions that do not allow stable liquid water. Observations with the James Webb Space Telescope have begun testing whether some of these planets have substantial atmospheres, and early results have already shown that at least some TRAPPIST-1 worlds do not appear to have Earth-like air. That is why red dwarfs sit at the center of the search without settling it. They are common. Their planets are detectable. Their long lives may offer time, but their close habitable zones, tidal locking, flares, and atmospheric risks make every candidate complicated. The search for life, therefore, cannot stop at size and orbit. A small planet near a red dwarf may look promising on a chart, but the deeper question is whether it has kept an atmosphere, whether that atmosphere has pressure and chemistry, and whether distant instruments can read those clues from Earth's side of space, reading the air of distant worlds. A planet's size and orbit can make it interesting, but they do not tell the whole story. A world may sit in the right region around its star and still be barren. It may be rocky but airless, warm but poisonous, or stable in orbit but stripped by radiation. To understand whether a planet might be more than a measured shadow, astronomers need to know whether it has an atmosphere and what that atmosphere contains. The method is called spectroscopy. Light carries information in its wavelengths. When starlight passes through gas, certain molecules absorb certain parts of that light. The result is a pattern, like a chemical fingerprint. During a transit, a small amount of starlight can pass through the thin edge of a planet's atmosphere before reaching the telescope. If the signal is strong enough, astronomers may detect signs of gases such as water vapor, carbon dioxide, methane, oxygen, or ozone. The measurement is extremely difficult. The atmosphere is only a thin shell around the planet, and the star can be thousands or millions of times brighter than the signal astronomers are trying to isolate. Clouds and haze can hide atmospheric features. Star spots and flares can complicate the reading. A planet may also have no substantial atmosphere at all, which is itself an important result. Silence in the spectrum can still teach something. Some of the strongest recent work has come from the James Webb Space Telescope. Webb does not make distant rocky planets easy to understand, but it gives astronomers a more sensitive way to test their atmospheres. Around TRAPPIST-1, for example, Webb observations have helped show how hard the problem is. An Earth-sized planet can be close enough for study and still produce a signal so faint that careful repeated measurements are needed before any claim becomes safe. The search for life has to remain cautious. No single gas proves biology. Oxygen can come from living things on Earth, but under some conditions, it can also build up without life. Methane can be produced by organisms, but it can also come from geology. Water vapor may show that water is present, but not that a planet is living. A possible biosignature only becomes meaningful inside a larger context. The star, the orbit, the planet's size, the atmosphere, the temperature, and the mixture of gases seen together. Earth gives the example, but not a simple rule. Its atmosphere contains oxygen, nitrogen, water vapor, carbon dioxide, methane in small amounts, and many other gases. Life helps keep some of that chemistry out of balance. From far away, a future observer would not see forests, oceans, animals, roads, or cities. They might see chemical disequilibrium, signs that a planet's atmosphere is being renewed in a way that deserves attention. That is why the phrase Earth 2 can mislead. Another living world may not be a twin of Earth. It may orbit a smaller star. It may have different clouds, oceans, continents, seasons, chemistry, or surface pressure. The deeper search is not for a perfect copy, but for another world where water, energy, chemistry, atmosphere, and time have come together long enough for life to leave evidence. Future telescopes may move the search beyond transit shadows. Coronagraphs can block some of a star's glare inside a telescope. A starshade, if used in a future mission, would fly separately from a telescope and cast a shadow over the star's light, making nearby planets easier to study. Larger mirrors and more sensitive instruments could help separate the faint light of a rocky planet from the overwhelming light of its star. The next major discovery may arrive through converging evidence rather than one dramatic signal. A planet in the right orbit, a measured radius, a reasonable mass, a stable star, an atmosphere, water vapor, carbon dioxide, perhaps gases that do not easily belong together unless something is renewing them. Each clue would be limited alone, but stronger together. So far, Earth remains the only known living world. Thousands of exoplanets have shown that planets are common, varied, and often surprising, but none has yet crossed the line from possible habitat to confirmed life. That is the honest edge of the search. The galaxy is full of worlds, but life is still known from one. The search for other worlds began as an old question under a sky of wandering lights. It passed through telescopes, timing wobbling stars, measured shadows, planet catalogs, and the first attempts to read alien air. It has not ended with another Earth. It has opened a sharper question. What kinds of planets can nature make, and how rare is a living one among them? The search for other worlds began with wandering lights in the ancient sky and moved outward through telescopes, timing wobbling stars, measured shadows, and the first attempts to read the air of distant planets. It has not ended with another Earth. It has ended, for now, with a sharper understanding of how many kinds of worlds the galaxy can make. Earth remains the only known living world. That makes it the first example, not the final answer. It is the place where air, water, chemistry, time, and life are already known to have met. Every other world waits inside evidence still being gathered. The stars are no longer only distant lights. Many are suns with systems of their own, holding planets too faint to see directly, but real enough to tug, dim, transit, and leave traces in passing light. Some may be bare stone. Some may be wrapped in air. Some may be frozen, scorched, gas-covered, ocean-rich, or stranger than any world nearby. For now, the question can rest. The numbers can soften back into stars, and the vastness can settle into quiet again. If you are still awake, another quiet lesson will be waiting when you are ready. And if sleep has already found you, you are welcome to stay here soundly, asleep in class.